I hope you had a good lunch. Looking at your faces, I think you did, and I'm sure you would rather now watch a movie and do your siesta. But I do have some slides that I will hope will keep you awake, and so please bear with me. Right, let's start. So I'm Valentin Olteanu, working for the Adobe Basel office on AEM, and today I would like to talk about the Sling memory usage and how applications are leveraging this system resource to deliver the expected performance. And I'll try to address this subject from a holistic point of view. And why do I want to talk about this? It's mostly because, from my experience, the physical memory, along with the CPU, of course, is one of the most important system resources when we are looking to operate at large scale and with highly performant systems. So, yeah, that's somehow normal, and it's because usually the code in Sling and in Oak expects to have the state in memory, so to have all the content cached and available, easily accessible in order to ensure the performance and to have, for example, really small response times. So, memory. Oh, that's a really, really wide subject. I think we could stay and talk about it for days. Like, you would think I'm crazy, and I would start talking, I know, about bits, addresses, and things like that. So no, I won't do that. I'll try to guide my talk around a few questions that I kept receiving whenever I was discussing with AEM users. And they were usually questions around how much RAM do I need to ensure my system is running properly? And then how do I have to configure my system? So how do I distribute the available memory between heap, non-heap memory, and so on, to have the right configuration, and again, to make sure I will never run into out-of-memory exceptions, so my process would not crash with risk of potentially losing even data. So these are the questions I will try to address throughout the talk. Just a spoiler alert. There won't be a simple answer to that, but I hope I'll give some tips and I'll guide you on what you can do to actually find the answer by yourselves, by inspecting, by trying out a few things with your deployment. So, what am I planning to do? I'll start by looking on the overall system and identify what is going on the system, identify the big components, big blocks of memory, and how wide they are allocated and where. And then I will deep down into a few of these components to get into even more details to see a little bit more. Just a little bit of information about what system I'm going to talk about. It's just a test system that I would use whenever I had to validate some performance issues or whenever I had to measure KPIs. And it's usually a standard AEM deployment, so just sample content that is running on a Linux VM. It has an 8 GB RAM. So yeah, nothing complicated. It's just a typical system running under a normal load without any problems. So as I said, my system had 8 GB, and I started looking into what is actually in the RAM loaded at a certain moment in time. And the first thing that I've noticed, and is normally expected, is that kernel itself takes up some space. In my case, it was taking around 200 megabytes for storing things like page tables, kernel stack, and so on. So you would find that in all the systems. I don't think there's any surprise here. The other thing that you usually have in a system, it's the tooling around that you have for monitoring, for, I don't know, deployment and so on, that also takes, consumes some resources. I was just using Logstash to push some monitoring data, so it was taking 800 minutes. Right. Now, the big elephant in the room would be the heap, of course. And it was taking precisely 4 gigabytes of the physical memory. Well, there was no surprise there. That's how I started my AEM instance by giving the max heap parameter to 4 gigabytes. The only thing that I could confirm is that the Java process was actually using the whole heap available, and it would reserve that memory in the RAM. It would commit it. So yeah, everything is, I suppose, common sense until here. But the rest is a little bit more obscure and not so well understood. And I'm talking about the remaining 3 gigabytes in my system. And this is basically the amount of RAM that the system itself will manage and will try to leverage it for different optimizations. So you'll always have some free memory available. The kernel will always try to keep a certain amount of memory in case you're, for example, starting a new process that will need to allocate it. So in my case, the kernel was saving 1 gigabyte of free memory, and the rest it would use it for the page cache. I don't know if you know it, but this is some operating system mechanism to help applications for caching files. So whenever an application would need to access a file, first it would be loaded into the memory and then served to the application. For whenever it will be reread, this cache will be used and it will improve the performance. So, for example, Sling applications are intensively relying on this mechanism for accessing files like bundle files or index files. But the most important user of this cache, I would say it's the segmentar, so your repository, that really needs to be loaded into this page cache in order to perform at maximum performance. Otherwise, you would see really bad response times. Right, so with this big picture in mind, my system was running perfectly fine. No memory problems, heap was enough, cache was enough. But this is because I found the proper balance between the two big components, between the heap and the page cache. And that ensured reliability and stability for my system. So, having this overview, I would like now to go a little bit deeper and talk, of course, about the heap. What would be in that big chunk of committed memory, and then try to understand also how the page cache is exercised by AEM. So, for the heap, to understand what is actually going on in the heap, I decided to go with a really standard and normal way of inspecting. So I've taken a heap dump of active objects in that heap and then loaded the heap dump in a memory analyzer, Eclipse memory analyzer in my case. And looked into it to see which objects are taking so much space. So let's see what I found in my 4 gigabytes of heap. Well, the first surprise, I think, was that the heap dump was a little smaller than the 4 gigabytes. Was, I think, when I took the heap dump, about 2 gigabytes. So yeah, that's normal because of the way Java is managing memory. There are always objects created and then discarded. So at a certain moment in time, you never have the whole heap accessible. Only a part of it is usable. The rest is garbage collectible or even garbage collected already. But you still need to have a bigger heap than what you actually use in order to have this space for creating and deleting objects. So I looked into the active objects, and I started separating these by components. And the biggest in my case was the segment cache, which is an on-heap cache used by the segmentar to store segments. So it's not the page cache that we're going to talk about. This was another component on cache that the segmentar would use. And this was exactly 256 megabytes. The other things, there were deduplication caches, again used by the segmentar, but this time for online revision cleanup to make it efficient and to make sure your repository stays small. I was surprised to see that, for example, the link checker in AEM would take quite a big chunk of memory, and it has some sort of cache, an array of links that would store and would keep references to it. Again, another cache used by the segmentar. There was Sling discovery, I think there was a reference to a JSON factory holding a JSON in memory. Not sure if that's by design, but it was there. Data store cache, Lucene cache for indexing. And then there were some smaller components, but that you could relate to and identify, that something like replication, the service registry, the servlet resolver, and of course there were some other parts that were much smaller. So it's a little bit interesting to look at these components because we could basically split them into 2 groups. There are usually the caches that are fixed size or size bounded that would never grow. For example, the segment cache by design will never go above 256 megabytes. And I think pretty much all of them have a mechanism to limit how much they grow. No matter how big is your repository, that's how much they will stay. And then there are the other components that, in my case, were smaller, like replication, probably the servlet resolver and so on, that are small in this case, but they can quickly grow, and their memory footprint will probably scale with the number of concurrent concurrent requests that you have on your system. So I think the takeaway from this slide is that whenever you are trying to size your heap, think about this baseline of caches that should always reside on the heap. And I know I've seen AEM starting with maybe 1 gigabyte or even 2 gigabytes of heap. And this is for this baseline. But whenever you need to support more and more load, think about scaling also your heap. And of course, if you have custom bundles, don't forget them when doing this exercise. OK, so the heap, I hope it's a little bit clear. And I'm going to go now through the page cache. And as I mentioned before, this page cache is an operating system mechanism. The application usually has no control over it. It has no control over whatever is in the cache. It just can leverage it as a transparent mechanism. So I focused for this page cache on the segmentar, because as I said, that's the most important part. And also I have the biggest knowledge on the segment tar. And I try to understand how the segmentar actually uses this over time. So I used a really nice tool called vmtouch that would tell me for each file which parts are actually residing in the memory, that are loaded and are available for the application. Oh, no, this way. So what you'll see here, I'll explain it in a little bit. I'll just let it play once to get an idea. I know it's small, but you don't have to really read all the details, but to get the big picture. That's why I've also added the colors to make it more obvious. So what is here? This is basically the output of this tool that I used, vmtouch, that for each tar file in my repository would show the number of pages that are actually loaded in the system. And it would also display by putting some small O in an array whenever that exact part of the file is in the memory. So it will make a nice visualization of which parts of my repository are in the memory. So I have here listed all the tar files. And I've also color-coded them. If you know a little bit about how online revision cleanup works, and I won't go into too many details, but you basically have 2 generations all the time in your repository. You have 2 copies of the content. And the yellow files belong to the old generation, while the blue files belong to the current generation that is in use. There's also a difference between the background colored files, which are files generated by the online revision cleanup itself, and the text color files that are created during request processing. So these store data generated by the requests themselves for the tasks running in your application. So what we have here as an initial screen, we have the old generation, and you will notice that there is no single page cached in memory. And this confirms that this old generation is not used and could be discarded, could be deleted at some point. And it will be, as you'll see later. And then we have the current generation, and there are some tar files partially loaded. The last ones are completely in memory. So yeah, that depends on how your application is reading which parts of your content tree. For example, there is a big gap in the middle that is not memory mapped. This means that the content stored in those files is not used. It's either it was overridden by newer revisions, so by data in the last tars, or you simply have some dormant content in your repository that you never access. There are things like, I know, disabled indexes or old versions of pages and assets that you never read. So whatever you see here mapped, it's basically constituting what would be called the working set of files in the memory. And in this first animation, you will see that the working set is quite stable. The animation is pretty boring, I would say. There are not many changes, just some pages are loaded. New tars are created and then are loaded, while older tars are evicted. So yeah, this is boring, and this is what you should expect from a normally running system, to be boring, not to have anything special. So yeah, playing again. This is throughout a few hours of a day. Now, in comparison, we would have this animation. So look what a party is there, huh? pages being evicted, reloaded again, evicted, reloading. So imagine every bit flipping there is a disk access from going and reading and then discarding that data and reading it again. So yeah, that reminds me my old desktop with an old hard disk. Whenever I would start doing something intensive, that sound, the song of the old hard disk. Yeah, this is what you should relate when you're seeing something like that. So this is basically a system that is trashing, a system that whose cache is not properly sized for the repository it has. If you notice, already there are much more tar files. They would not even fit in one screen. The list would be even longer. And I also, to get this animation, I would put much more stress on the system to have that. But if you're seeing that, and you can also get a summary by looking at the major page faults on your system. If you have that in your system, it's really bad. You should look into scaling up or reducing the load to bring it back to the boring state, because this is not nice. OK, so there is one more animation like this that I would like to show, because it's a little bit interesting for understanding the online revision cleanup. And yeah, I think it would be nice to get the big picture. So I let it play once and then try to explain. So we're going to go at the beginning. And we are starting basically with the initial picture, where we have the old generation, the old copy of the content that is not used, while some parts in the current generation are in memory. So what is happening at this moment in time, basically, when you see the second group of yellow tars, that's when online revision cleanup starts. And what it does, it will read the blue tar files. You can notice that the tar files are very linearly read, so loaded into memory and then evicted in a really monotone way. And the revision cleanup would create a new copy, the yellow one, with the same content, but in a much more compacted way. So if you pay attention to the blue tar files, you would see this scrolling effect throughout them. Now, there is this moment. If you've seen there's a jump there, that's the end of the online revision cleanup, when the old yellow, so that's the old generation, is deleted. That could have been safely removed since a while, but that's a good moment to actually delete it. So it's deleted. It was not used anymore. The interesting thing, and this explains why you need two generations in your repository, and is that after online revision cleanup finishes, so there are already tars, a tar file created by normal request, you would see that now there are both generations being in memory. It means that both data from both generations are used by your system. And that's because you have maybe long-running tasks or just requests that are still processed and that still hold references to your old generation. But this clears out, and in time, after online revision cleanup finishes, the old generation is evicted because tasks finish, and the new generation, which becomes current, arrives to pretty much the same state as before compaction. So this is how online revision cleanup works, and that's why it needs to keep both generations. Yeah, that's mostly it regarding the online revision cleanup, regarding the page cache, actually. And I would say that the takeaway is that you need to size or to let enough available RAM to the system to be able to store the content, the tar files that your application is using. So, almost in time. Coming back to the initial question, to how much, of course, the answer is it depends. There's no simple answer, but as really generic guidelines is that you should scale your heap according to the system load, and your page cache should take into consideration how big is your repository, so your segment store, and more specifically the working set. So you would not look at the entire size because you usually have two generations, but ideally you should give enough memory to store potentially one full generation in case your application is fully using all the content. So I think that was mostly it. You have the content and some scripts that I use to get this data. If you want to play with, they are available on GitHub.